So hello, welcome back once again in the evening session of DSA. So in previous session we solved the problems that are number of islands, okay, detect the cycle in the director cycle and topological sorts, okay. So in this session we try to solve this two question, okay, like we try to solve shortest path and the Nakshatra. So let's see. So how we will do? So first of all, we have to understand what is the shortest path in the unweighted graph. How we solve? Okay. Hello. So sorry for inconvenience. So we try to solve this the shortest path in unweighted graph. So in unweighted graph, every edge has some cost. So unweighted graph. Okay. So in unweighted graph, each edge has edge has we can say that. So each. So I think I have to do this thing. So okay, in this each of edge. Okay, so each of edge have a cost of one. So that's why it is like we solve in this one. So let's try to solve this problem. So here we can solve. Okay. So in this what is how to solve? Shortest path in an unweighted graph. So for solving this, first of all, in unweighted graph, every edge has this is node is connected to this node. We connected this node, and this is connected to this node. Okay. So some have particular values, so 1, 2, 3, and the fours all have. But this weight have some all the value have 1, 1, and 1. Okay. And the shortest path mean minimum number of edge from the source to destination. So just imagine we have 5, 6 connected. So in this we can say that in this we want to reach from the source, and this is the destination. So we can choose any of the parts. So we can choose either this path to reach at this position, or either we can choose this part to reach the destination. So this one is the minimum shortest path. Okay. So in another word, we can say that the shortest path is equal to minimum number of edge from the sources. So minimum number of edge from this source. Okay. So for which algorithm we are trying to use? So the algorithm that we are trying to use is like BFS. Okay. From BFS we can explore node level by level. Okay. So in which we can explore the node level by level. Okay. Level by okay level. So we understand that in for solving this one. So solving this one, no, green. So solving this one, we need solving this one. We use BFS, okay. And why BFS give the shortest path? Because BFS travels in the when we have something. So level by level. So this is a level 1, this is the level 2, and this is the level 3, and this is the level 4. Okay. So we can see that in level 1 we can say that at zero level, sorry, at zero level only 1 is there. At 2 is at 1 is equal to 2, 3 and 4. At level 2, 2 only 5, and level 3 only 6. So from the BFS we reach like first time, okay. So when we reach this node, okay, so any other path cannot be like shorter. So if we want to reach at this position at 4, so we can only like go to like one jump we needed, okay. Only one jump is needed. So down is not working, it's at yellow color. It's clear. So this is the yellow. So we can see that from the only one level is needed to reach at this destination, okay. The first time BFS visit a node and it reach it using the shortest path, okay. So okay, so for the C++, what we are needed, first of all we needed n vertices, okay, m edges and source and the destination. What are these things are given? Edges, okay, so these are the vertices, these are the edge, okay, edge, and this is the source, okay, or destination. This is, these things are required, okay. So the uh logic is that to solving this question, logic for this one is that first of all we like maintain a queue data structure. So we maintain a queue, so QUE integer. So in queue, like we use queue data structure. So for that one I have to like uh, write the code for this one, okay. So we are trying to solve this problem. So at least we have some code. So from that we understand. Okay, this is the code which required to like which is very much required to solve this problem. Okay, so first of all we have to see this one. Okay, first of all we focus on this thing, like initializing the things. So first of all we have to like maintain the codes, like maintain our this array in which we like where we are reachable, okay. So this is like distance vector and the queue, okay. And we like write for this like 1 2 3 4 for reaching from the source is equal to source becomes 0, okay. First of all in that case, so distance of source is equal to 0, we push that. And in queue we push this source that is 1, okay. Source is pushed and the till check queue is empty or not. So first of all, 1 second. sorry, one second. So in which we like push the source node, and for that this is the front. Okay, so this will be like node's fronts. Okay, so we pop this value. Okay, pop this value and check its neighbor. So if neighbor, and we also check if that in distance the neighbor is -1. In that case we increment the distance by 1. The distance of the node is like 0, so we add, so it become 1. Okay, and push that neighbor into this one, so like 0, 1, 2, 3. So in that we push the value, so it become 1. Okay, okay, so this loop is continue, and in that we will fill the different levels. So different level. Okay, so this is like, from, if you want like source to distance from this one, so we see the example that is 0. Okay, 1, 2, 3. Okay, and 3 and 4. Okay, so if we maintain a distance table, if we want to like see, so if we want to see this thing, what we think, what is the distance between source to like uh, source to all the nodes. So in that case, this is like distance of source to source is 0, with source to 1 is equal to 1, source to this distance is also 1, and source to like 3 is equal to 2, and source to this position is 2. So this is the output we want to get, and by this process we like achieve the process. So in that case, if we under distance of this neighbor is equal to distance of the node plus 1 level. So that's why we plus this one. Okay, and push this. So this is a pretty straightforward and the simple question. And the another question, that is like Dijkstra algorithm. So what is Dijkstra algorithm? So we have to understand. So finding the shortest part in the weighted graph. So we understand the unweighted, and for the weighted we have to see. Let's see. Uh, let's see. What is Dijkstra? So in this, we can see that the shortest part for the weighted and for the non-negative weighted plus and non-negative wave. So in this case, the use cases of the mean, heap, relax, edge, and keep updating in the best distance. So like, let's see what is inside the Dijkstra algorithm. So like Dijkstra, the graph is, so this is Dijkstra algorithm. So in this case, we want to need, like, first of all the graph must be weighted. Okay, for the weighted, and edge the edge is weighted. The edge is weighted and weighted. Okay, weighted and non-negative. We know that non-negative. So we understand all this thing. No need of shortest path from source to all nodes. So like, so in that case we have to find this one. Okay, let's see. We have like one. Okay, like if A, this is B. Okay, this is C. Okay, and this is D. So in this is like 4. Okay, this is 2, this is 3, and this is 1. Okay, so by this one, find the like shortest path from A to every node. So A to every node. So what is the shortest path? Why BFS in this case fail? Okay, so if you want to like consider, if you want to do level wise, so in this case BFS, why BFS fails here? So if we want to reach like just imagine the cost of this one. We take another example why BFS is fail. So if A to B is the cost is 100, okay, so this is the only first level, okay, 100, and A to C is 1 and C to A is equal to this is 1. So if we want to reach at if we want to reach this like A to B, so we choose like shortest path. This will be this minimum number of nodes, like a minimum number of edge we have. So we choose this one in the BFS case, okay. So in BFS case, we choose this path because we know that for the BFS, like minimum number of edge. So minimum number of edge we needed. Okay. So minimum number of edge needed. So this will be the minimum number of edge. Okay. So but its cost is equal to 100. But this is not the shortest path. So this is the shortest path. This if we take this path, so the cost is equal to only 2. Okay. So that's why the BFS fails here. So in that case, BFS fail in this case. Okay. So for that one, so as the BFS fail for the weighted graph, so we consider another method to solve this one. Okay. So always process the node with their smallest node distance first. Okay. So we have to process the another node, but we have to first of all we have to know the smallest node distance. Okay. Node and the distance. Okay, so we want to make a distance table like this one. So if source is in some graph, if source is 0, so in that case we have to maintain from source to source 0. To 1 we have to take 4 weight. Okay. We want to go to 2, we take 1. We want to go at this position, we want like infinite. So this type of things we have to do. Okay. So let's see. So solving the diagram, so we have to make space. This over here. Okay. It's first for this one. So hence, so first the algorithm steps are needed. First of all, we have to initialize. First of all, we have to initialize. So in that case, we need some priority queue. Okay. Pair. So mean heap. So in this case, we need a mean heap. Okay. Mean heap. So in a pair, so we want like node comma distance. So in this case we need node and distance. So this is like pair of things. Okay, this is pair and this is like distance. Okay, pair int comma int vector. Okay, vector of something. So how we write like mean heap. So we know that how we write mean heap. So in the mean heap, so we write like this one. So priority underscore q, one pair of integers. Okay, if you want a pair of integer int comma int, so this thing we have to write in vector. Okay, in that case we need a vector pair of int comma int. Okay, comma. Okay, and the greater of inside same thing you have like a pair of int comma int. Okay, we have to close this one. Three time to close and write pick you all these things. Okay, through by this one we initialize the mean heap. Okay, if we like initialize the mean heap, so first of all we have to initialize this value. First of all we have to make distance is equal to 0. So and distance between source is 0. So if we maintain a distance matrix, a distance array, okay. First of all, we make a array of from the source to each node, source to each node. So like this one is equal to 0. Okay. All are initialized with the infinity value. Always initialized with the infinity value. Okay. So first of all, I like change the value. So I change the value to like 0 to source. Okay. Because source of source is equal to 0. In the priority queue, you put like a mean heap always return the minimum value at the front. So that's why we use mean heap. So in that case, a priority queue in which we like initialize the distance and the nodes, okay, and we run this while loop till, and from this one auto this d dot node will be extract the pq dot top. So this pq dot top value will be the front value, okay, and it's pop it. And if we check if this distance d is greater than the the node the node that we are talking about, the nodes distance we have, if bigger, then we continue. We don't like change of this value. If d is equal to, just imagine d is equal to 2 and its value is equal to 0 and this value is equal to 0, so why we need to change this value? So in that case we continue this thing, okay. And okay, so where we are, so and if, and okay, so we check the neighbors things, okay, auto neighbor, who is the neighbor and what is the weight. So in this way, in this case, this is the neighbor and this is the weight, okay. So we check in the adjacency matrix. In adjacency matrix there is like neighbor value is given and then this weight is given. So in that case we find a value. If we check that distance of that node plus weight is less than distance of that neighbor, okay. So in that case we have to update distance of neighbor is equal to distance dot node plus this one, okay, and push that distance of neighbor and that neighbor into the pq and run this loop until we finish, and then we have to return the value, okay. You might confuse at this position, but this is like clear thing. So what is the like structure of a density matrix? We see that there might be a like first of all we write the in a density matrix, there will be like for 0 comma 0, for 0 its neighbor will be written as a 2 comma and its weights 3 comma and weights. So in this density matrix is written as this one. So that's why we never find a neighbor. And first of all in distance table we check the node plus and the weight of this one is less than if the distance of that neighbor. So in that case we update the value and push into the priority queue and finally we return. So this is the simple Dijikshetra, okay, algo, and it is used for the weighted graph, okay. It is used for the weighted graph. So these two code are very much simple. So we try to finish this third code also. So that is all about like clone the graph. Like we want to like clone the graph. So for the cloning graph we can use like BFS and DFS. Clone the use BFS and like DFS with the hash map for the original node to clone, okay. So let's see cloning of the graph. Okay. How I clone the graph. So let's see. So this is a very common BFS and DFS question. So mostly asked by different company. So we are given with the nodes and connected graph. Okay, node and connected. We have to create a deep copy. So we have to create. So this. So we have to do the deep copy. Okay. we want to do a deep copy of this one. So like original graph look like, so original graph look like 1 to 2, this is 3, and this is 4. Okay, so that's when we have to like we have to do clone. So it look like 1, 2, 3, and 4. Okay, yes. So this look like same. So every node is newly created. Okay, so like original node 1 is not is equal to like original node is 1 is not is equal to this one. So this is one is a clone. So but the structure remain identical. The structure remain identical in this one. Okay, structure remain identical. This case structure remain identical. So but why it is so tricky, and so they ask by many interviewer. Okay, this is just if there is a cycle between this one. So we see that 1 2 3 and the cycle. Okay, but if you want to clone, but if we keep cloning blindly, okay, so it will be like return. So like this one. So if these things are like this one, so it is 1 2 2 2 3, and this is like graph. Okay, so if we clone, it will be return like 1 to 2 2 say 3 3 2 1 1 say 2 2 3 1. So it will like cloning infinite in recursive manner. So we need a visited things. Okay, so like we reach to this position, so we need a visited map. Okay, to do this one. Okay, so we need a visited map to we like handle from the this infinite recursion. Okay, so infinite recursion. Okay, so for every original node, so we are denoted as the old node. Okay, and for every we created old node, this is the old node, and every new node we created, we are known as a new node. Okay, for storing the things, so for the storing the things, we can use like unordered map. Okay, map in which we have node and this is like graph. So node start node. Okay, this is the map. Okay, so this is what we look inside the map value, and we have to do. So let's see. So like step by step procedure, and we can solve using like DFS. So we use the DFS code. DFS like this is the DFS code. So let's see. So first of all, we created. First of all, the step is that so if the node is already cloned, just return mp dot something. So if any node, so if the first step is that first step is that we created an order map in which we stored like nodes and nodes. Okay, and node star. So this is like we are like integer vector all these things in a BFS in which node is that some particular node. Okay, so if mp dot count, if we like do mp dot count, okay, that node. Okay, that node inside the mp. So in that case, return the mp of that node. So if we nodes mp of that node. Okay, or like in that case, we created a clone new node, and then clone, that is new node and node value. Okay, okay, so mp of that node is equal to clone. Okay, assign, and also check for its neighbor. So these two is important topic. We created a clone, so we want to create a clone that is look like that look like a map. So in that case, we have created new, that is node. Okay, by inside this node, the value of this previous old node value. Okay, so this is thing. And what we assign if MP of that node value is assigned to this clone value. Okay, this clone, and find the find the neighbor of this node. Okay, like auto, we can also auto node neighbor. We write node neighbor. Okay, nodes neighbor. So in that, clones dot neighbor dot push back DFS of its neighbor. Okay, clones dot neighbor, like if we created clones dot neighbor, in that return the neighbor, and finally we return this value clone. Okay, if node is null, simply return, and otherwise this one. So like we created the clone value. Every time we add this value, we create the clone and we put the value. Okay, again, if it is never, then create a node and put the value. If we created the node and put the value. Okay, this creation of the thing and the putting the value inside, like this one. Okay, so this is the thing that we use for cloning any graph. Okay, so by this process we can clone the graph. Okay, so this will take, so if we want to like uh run the like pattern, so we can do, but we can do. So if the same thing happen if we use like BFS, in BFS we know that if we make for the BFS, let's see the BFS code. The BFS code will look like this way. So like BFS code. So BFS code, let's like drill down the BFS code. First of all, we see that if node is sorry. So if node is null, so in that case we return null. Okay, an order map for storing the this value. Okay, in the BFS, BFS stands for the queue. Okay, so if we see BFS, use queue. Okay, so queue, and inside the queue we have to store the node. Okay, we have to store the node, and if map of node, so in that case map of node is equal to new node and its then value. Okay, map of this node is equal to new node and this node value and dash. Okay, this one dash. Okay, and we push that node, and we push the node inside the queue, we push the node inside the queue, and again like in front we need like extract this value 1 and pop it from this one. We find nodes neighbor, so like node neighbor, so current dot neighbor, by this way we can find a neighbor. So if mp dot count this neighbor, if mp dot count, if there is an like this one is equal to 1 dash. Okay, so if mp dot count this neighbor, if not available, so in that case like mp of neighbor, that is 2, we put new node, that new node, and then put the value 2 dash. Okay, and push that neighbor. Okay, by this process, and finally by doing this, if we like if it is not there, if it is there, so mp of current, so mp of current dot neighbor, so mp of that current node, that is 3 dot neighbor, is equal to is it mp dot current dot neighbor dot pushback is equal to mp dot neighbor. Okay, it becomes neighbor of this one, and finally we have written the mp of nodes. So in that case we have written the mp of nodes. Okay, so in this case we simply return the clone value, or in this we have written the mp dot node. So these are the two way through which so this one is like DFS. Okay, DFS, and this one is a BFS. So by two process we can clone the clone the graph. Okay, so thank you for joining this session, and we are left with like 3 to 4 question. Okay, 3 question that find the bridge or articulation, all this thing. So okay, we try to cover this thing in the next lecture. Till now, bye bye.